known David for a long time, and he's also has a physical oceanographic background and has moved in a different direction. Hi, David, why don't you can tell us a little bit more about yourself, I guess. Why don't you take it away?
Sure. So my name is David Stuebe. I've known Rich from back in my days at Woods Hole, studying ocean physics, like he said, and all through a circuitous path where I now find myself doing electric load forecasting for Camus Energy. Camus Energy is a green tech startup looking to do decarbonize the electric grid, basically. And so my job at Camus is to forecast the load or generation at any aggregated level in the grid, from your home electric meter up to the transformer, up to the substation and system total load. And all the generation from rooftop solar, wind, and all the load from HVAC is all highly weather dependent. And so weather is a tremendously important input to the machine learning models that I run. For over 2 years now, we've been very successfully using the HRR surface data through NODD, and using Kerchunk to do scan GRIB and then multi-Zarr to Zarr in a like recursive nested way to go from the individual hourly file up to a daily aggregation to a monthly aggregation. And we've been very successfully using that to do forecasting on up to millions of meters for a given utility company. Our customers are distribution utilities. So we were looking to do a V2 of this, and I've spent I don't know, probably 4 or 5 months now, mostly focused on this. And there were a couple things on sort of our wish list. First was we wanted to get a lot more of the HRR data. So we wanted to get the sub-hourly as well as the surface data. And that means we get 15-minute time steps instead of hourly time steps, as well as some average variables that are really important. So get more layers out of those GRIB files than we've been able to previously. And we wanted to do all this stuff much faster. We were running huge compute bills. Now that we had our sort of end-to-end pipeline and all this stuff working, we wanted to go back and optimize it to cut our cloud costs. And there were 2 places to do that. One was that aggregation step is actually pretty expensive. Running that full scan GRIB over the HRR GRIB files, they're hundreds of megabytes for some of the GFS files that we're now pulling. They're like 500 megabytes. They're really huge. And then the other is in running the actual machine learning models, the I/O that we were doing, calling interp on the X-ray data set that we were interested, the variables we were interested in, and calling the X-ray interp operation was serializing the I/O. And for the life of me, I couldn't figure out how to get Dask or any of the parallelization sort of built into X-ray to do that without doing some kind of bespoke. I should be sharing my screen. Do you guys not see my screen?
We're seeing your screen, but not. Are you using any slides or just the?
Yeah, I'm just talking.
Okay.
I was going to have slides, and Rich bumped me up by 3 weeks on Sunday night, so I apologize for just yakking at you. But I will be sharing something practical and useful in just a second here. That notebook. I was just trying to give a little more context. And so we're doing this machine learning forecasting, and the I/O is just crushing us. That it's the serialized I/O, and so I've got a sort of candidate approach to parallelizing the I/O inside Zarr that I'd like to share and get some feedback on, and think about, like, is there a way that could actually become part of Zarr 2, or if not, maybe at least a benchmark for the performance we should get in Zarr 3, where things are really concurrent in a better way. So with that, I will start running some stuff in a notebook here and show you what I've done. So this is all available in this repo here that's posted in the notes. It's open as an open PR right now, but you should be able to grab this and follow the setup and run along with me if you're interested. So to start with, we can grab 2 large GFS forecasts. I've been using the GCP ecosystem. It should work equally well for AWS, but I haven't tried it there yet. And the first thing you'll notice is what I mentioned here, that I wrote this GRIB tree function that is now part of Kerchunk in the 2.4 or 2.4.1 release that's in the notes further below there from last week or this week. And GRIB tree allows you to build a extract all the layers and build one X-ray tree rather than a data set with a few variables for a single set of layers. And if you're not familiar with GRIB layers, they have sort of vertical height-like layers, or it might be pressure coordinates, as well as time step layers. And so I built this function in a way that made sense to me. It's the simplest thing I could figure out, which wasn't very simple, to allow you to build an X-ray data structure that would work for the GRIB data model. And as you're seeing here, this takes a while to run. It's pulling two fairly large GFS files, and this is running on a fairly beefy instance in GCP. I've got a 16-core, fairly heavy E2 16 machine here, E2 standard 16 machine here, and it still takes a while, and it's very much serialized. It's sitting there chugging away at 100%, grabbing, prefetching all the data with FS-spec, and then parsing the messages using CF-GRIB, and building these groups, and it produces a sort of Zarr-like reference data for each group in the GRIB file. And then we're going to turn that into a tree where vertical coordinates get aggregated, but each variable ends up with its own nested groups inside the data tree. And that's really necessary, I found, because even variables that share coordinates like height above ground don't actually have the same height above ground necessarily. They don't have, some have 7 height above ground values, and some have 5, and they might be different. So I couldn't find a way to build one data set. So I ended up using X-ray data tree, which has been very successful. This should finish in a minute here. Otherwise, this is going to be a silly looking presentation. But I'm fairly confident it'll come through. And I can start talking through what we're going to do next. So we'll see the GRIB tree here. And then what I found is that by separating out the, that's a good sign, separating out the sort of static data that describes the data set, the attributes and the shape and so forth, from the individual time step chunks, we can gain a lot of value. So here's the GRIB tree that we're building. And this is already, again, part of Kerchunk in the latest release. So here's a group for each variable. And let's scroll down to something interesting. I like DSWRF. That's my favorite. Where is it? Downward shortwave radiation. So we go through one nested group for each of the layers. So this is the average, as opposed to like the instantaneous value. And then we have a group for surface, and then inside there is the data variable DSWRF, and we can see all its metadata here. So this is like a very verbose sort of exploded view of this thing. There's probably a better way to do this, but I would love input from others on how to better map GRIB to X-ray or X-ray data tree. I'm gonna scroll through fast here, all 99 variables. We can look at one that might be more interesting with the layers. Where's U? V, that'll work. So this one is instantaneous velocity, and we have 10 groups, one for height above ground, one for height above sea, one for isobaric and PAH, and these all have different vertical coordinates, which is why you can't smash them into one data set. All right, so enough about that. What allows me to do this stuff much more quickly then is separating this stuff out into the static metadata, as I mentioned, and the dynamic stuff. So if we pull the stuff that's unique about the data set out here, and I realize I should probably scale this up a bit for you folks. But if we pull out the variable name and those group attributes, the type of level and step type, along with the time coordinates, the step, the level, and the runtime and the valid time of the forecast, along with the URI, offset, and length, we have this, sort of table of data. And this is very similar to what I think the Zarr team is talking about doing, and what Martin Durant has done with Parquet storage for Zarr. So this is nothing particularly unique or insightful. What is exciting, though, is being able to store it separately and then recombine it. So I really like that view. I appreciate the value of being able to append to an existing Zarr store in Parquet. For me, operationally, I really prefer not mutating data structures. So for me, I'd like to process a GRIB file and spit out, this kind of sort of index metadata, and then build the Zarr aggregation I want at runtime, rather than mutating data structures. I'd rather let a database that manages my rows handle the mutation. And so we'll see that in a minute here, and I can talk more about what we're doing operationally at Camus. But here I've then separated out just this deflated Zarr store, and let's take a look at that real quick. So that should be a big old dictionary here. And you'll see it has, Z group and Z adders, but no actual, data values except for coordinates. So it'll have Latin long in there, but no data values is what we've done. Okay, how do I get this to not scroll both ways? I'm used to using Colab where the scroll works a little differently. Okay, so the first observation that was exciting is that the IDX files that go along with GRIB files have a lot of the same information in them. Well, not a lot, but some of it. They have the offset. Oh, that wasn't what I wanted. They have the offset of each, or sorry, the length of each message stored for you handily in. Is it the offset? I can't remember which it is. I think it's the length. Anyway, they have enough metadata that you can reverse engineer the offset and the length for each message.
Those are the offset. The length is to the next message or the end file.
Thank you. You're right, because the first one's 0, so it's the offset. But if you take the difference between each successive message, you can get the offset and the length, and then use the file size for the last one. Unfortunately, they don't have quite the same metadata structure for these names. They give you this sort of English parse name of the hybrid level and hour forecast that you'd get from the GRIB CF reader for instant and type of level and that sort of thing. But you can build a mapping, and they are one-to-one for a given, for the 6-hour horizon forecast. You can build a one-to-one mapping between the IDX file and the metadata you would have gotten from the CF reader. So let's do that. So if we parse this IDX file, I can get offset and now the length as well. As I said, you can pull out this like crazy adders string that we had here for the name and the sort of levels associated with it. And then I started pulling out, CRCs, CRC32s and stuff to do some metadata sanity if something got screwed up. Some of the accumulation variables don't work properly. I think the accumulation variables tend to have both a current time step accumulation total as well as a run start to now total. And so those names are not unique, but for all the other variables in GFS, GEFS, and HRR for the products I looked at, surface, sub-hourly, and for all the things I looked at, the only ones that I've had problems with are the accumulation variables, where you can't distinguish the IDX metadata is actually the same for those accumulation variables. But for everything else, this seems to work nicely. So we can build our mapping, and let's take a look what we get. This is actually going to go compare it to the GFS file, the GRIB file. So it's going to take a second. It's going to go read the GFS file again and compare message by message in the GRIB file, the IDX data to the original GRIB file and build this mapping so that we can translate any IDX file for the same forecast horizon into the GRIB metadata. And once we have that, we can do some really cool stuff, which I'll show you in a second. Should have started that cell before now. Sorry about that. We're going to see next are, some stripping out there to deal with the accumulation variables, deduplicating with keep first. And then I'm going to run over a longer range here to get 120 GFS files for a month. So they're four a day for 30 days. Grab all the 6 hour. What did I get? The 0 to 24 by 6, and I'm looking at the what horizon am I looking at? Where's horizon set? I don't know. We'll see it in a second. Did that finish yet? Nope. I think the 6 hour horizon. Yeah, the 6 hour horizon here we're looking at. And that should run in about 20 or 30 seconds at most. I've seen it as low as 18 seconds, depending on how fast GCS is feeling on a given day. Come on. Live demos are the worst. I've run this I run this operationally now with Camus, and I've been pushing these Parquet files that we create from the IDX data into BigQuery, and then using BigQuery queries. There we go. So here's the mapping. So now we've got the data from the IDX file mapped with the where is it? This crazy adder string that's in the IDX file, mapped to the name, level, step, time, invalid time, step type, all that you would get from the GRIB file. And these mappings seem to work pretty well. When I use this operationally, and then here's mapping from the IDX. We can get a table that looks very much like what I had up above from parsing the original GRIB file. We can do that for, as I said, for 120 GFS files here, and I'm claiming this will be done in about 30 seconds. But as I was saying, when I do this operationally for Camus, we're pushing these indexes into BigQuery by writing Parquet files to GCS, and BigQuery does all the deduplication and updating for us there, and that seems to be fast enough in a really nice way. There we go. So that there's 88,000 rows from 120 files. Let's see what we got. So I built a kind of crazy interface here to describe how you would recombine these things. I would love some help from the community. You can see some pretty extensive tests now in this PR as of this morning for how all this works. But I built my own view on how aggregation could work to sort of describe, hey, I want to describe this FMRC chunk. I want to slice by forecast horizon, or I want to slice a particular valid time, or I want to slice a particular runtime. So you describe some fairly arcane date range structures here, and then you run this method here that's quite fast. You open the data tree, you get out as a result. And here we've only selected out two variables, DSWRF and 2TM, but it works for however many variables you want. And here's that same data structure we saw before, but now the dimensions are a little bit different. We've got one model horizon. You can specify 1 or 10 or all of them. 120 valid times, and the lat and lon have stayed the same from the original data set. And then let's see what we can do with this. Here we go. So there's pulling out a time series for the first 10 values pretty quick. And then here's pulling out some pretty pictures for different time steps. And you can see the sunlight moving hour by hour there, which is pretty neat. So yeah, we're doing this operationally now, and I'm pulling time series up to like 28,000 values or 35,000 values, like a 4-year hourly data set. And that gets a little painfully slow. So the next thing I wanted to work on was that. Rich, is it kosher to like stop and take a minute to ask questions about this part of the presentation and this piece of what we've done here? This is very high level and going really fast. There's a ton to unpack here, but I'm hoping that this is like exciting and motivating to engage on, not like a full explanation of everything I've done here, and hoping folks might have some questions here, or should I wait until the end?
I'd say go ahead and take questions here. Like, we have this, I don't know where this policy came from of like only recording the talk, but like sometimes the questions are more almost as interesting as the talk.
Yeah.
So let's just go for it and record the whole thing.
Great.
Or at least record this. Yeah, go ahead. If people want to ask questions here, feel free. All right, nobody wants to be on the Zenodo. That's okay, keep on going.
All right. So the next thing I want to do was make it run faster for our machine learning models. Again, this is something that we spend thousands of dollars a month on GCP compute costs. And what I observed is that within Zarr, the IO gets serialized. Here I just pulled out 120 time steps in, I don't know, what was that, a couple seconds, 4 or 5 seconds. Normally that takes several minutes. This is actually so fast. I don't have like a benchmark to show you, but I show you what I did, and it's not anything cached. You can pull out more of them, and you can see it's going to change the size of the shape of the chunk that you get here if you pull 2 by 2. Now it's going to pull 105 by 85, but it's still quite fast. And you get your well, now it doesn't make a nice time series. It does some crazy bar plot or something, but and so this is really exciting for anybody who's worked with this stuff before. I don't have like a like apples to apples benchmark comparison to show or anything, but for anybody who's used to trying to grab these through Zarr with something like an interp function or get a time series, even just getting the whole data set. That should work. There we go. And that's with all the data now. And it's really fast. So what I observed in looking at Zarr is that there's this one point of serialization in the core module called chunk get items. And there are 2 serial for loops over the keys that you're fetching for your data set. The first is, inside an if block, depending on how you're reading it, whether it's BLAS-C encoded or whatnot, you do a for loop to get the data and build up this big in-memory dictionary of byte buffers. And then down here, there's this, second for loop to decode it. And no matter how smart you are in how you're reading these things using async or some other, Rust implementation, whatever you're doing, this for loop, it might be a list comprehension, but it's still a for loop that's going to serialize that, because there's no await or anything here. This is, each step in that for loop is fully serialized at this point in the Zarr 2 stack. So I just smashed them together into a parallel method to get the C data for GRIB spec only, for GRIB codec only. But I think this generalizes, which could be kind of exciting if someone can figure out how. And so I get the C data for the chunk, I decode the chunk, and then I insert it into the output array, which is sort of what the chunk get items method does, really. But I can do it in parallel now and use mem-mapped IO for the output array. And this now runs really, really fast if you can tune it right for the batch size and so forth. I chose joblib because that's the framework that we use for parallelization with our scikit-learn machine learning models. This is not at all general. This is nothing you could merge into Zarr like this, but gosh, I guess my hope is that maybe it could be a sort of benchmark for what we should hope for in Zarr III in terms of performance natively without having to hack it like this. And for anybody who has this problem and really wants to make it go faster, you can look at this chunk get items method and maybe use this as a bit of a roadmap to figure out how to parallelize the path, the particular if part of the if block that you're in. So I hope that might be helpful to other folks. And if there's some way to get this performance without doing this hack, I would love it. I'm not proud of this, but it was something to share because I haven't seen anybody else talk about a way to do it better. And if there is one, I would love to know what it is. But this is what I've done that's potentially saving us thousands of dollars on operations like this that are currently serialized in that for loop.
Okay. Is that it?
That's it.
Awesome. Yeah, we'll stop the recording now.